So let's talk about this one, Ensemble Learning and Random Forest. This goes through the models in the chapter, basically. There's an online repository that has Google Colab set up with this, but I've made minor modifications in it and added some stuff so we can have some flags to turn in, is really all I've done, and picked out the ones that work. So here I prepare a data set to make the moon-shaped data set, something we use quite a few times. So there's the moon data. And unlike the book, their Colab has you do things that don't have anything you can see. I always try to make mine so they produce a graph or a number or something so you can tell it works. So here it is. It made a nice moon-shaped data set with blue dots up here and green triangles down there. And they overlap somewhat, but clearly you could draw a reasonable decision line between them. And now we're going to classify it within Ensemble. So the three different predictors are logistic regression, support vector machine, and a random forest. And here's how you do it. It is extremely simple. You import random forest classifier, logistic regression, and SVC, and then a voting classifier. And then you make three estimators from each of them, and then you train them. You train it on your X-train and Y-train data, and then you score it on your test data. So we'll get accuracy of the individual estimators, and then we're going to run the voting classifier and get its score. So it's amazingly easy. It only takes a few lines of Python to do this, because the libraries, the sklearn library, just has all these algorithms in it ready to go. And we're just running it with the simple, mostly default conditions. And we specify the random state. This is something we always do in these projects. Otherwise, I couldn't give you a flag, because the answer would be random. This way, if you use my random state, you'll get exactly the same answer I got, and then I can use it for a flag. So here we go. The three classifiers have this success rate, 86%, 89%, and 89%, but the overall thing is 91%. So that's the point. You have three classifiers, and when you combine them, you get better precision than any of them alone. That's the idea. All right. So now we're going to use, this is hard voting. Now we're going to use soft voting. So again, you just combine the classifier. This is how you do soft voting. And I guess we're using SVC for the soft voting. I'm not quite sure exactly what machine learning model we're using for the soft voting there. But here's the soft voting, and that gets you from 91 up to 92%. So as you'd expect, there probably is a smarter way to combine these three than to just have them each vote and take the best 2 out of 3. This does something smarter, like take the analog output of these and determine how much to weight each one. All right, now we're going to do bagging. This is what I talked about before. So we're going to have the training set and make multiple samples of it by random sampling. And all right, and this is going to make 500 trees, 500 estimators, which seems crazy, but that's how it's going to go. All right, let's take a look and see. And again, we're going to print out the accuracy at the end, so we have some numbers to see how good it is. Now you can see which command is being executed. So here it is, done the prediction, and now it's done. Okay, so as you get the signal, this is one decision tree, I think, and here's the 500 decision trees with bagging. So 500 of them combined create this, and the bagging classifier is 90%. So it's not as accurate as the 3-vote classifier we made before, but it's pretty good. So a single decision tree overfits the data. This is a ridiculous decision boundary with ridiculous things like the ones in here are red, but the ones outside it are green, which obviously is just fitting the noise, not the real trend in the data. And but the bagging ensemble has combined them and pretty much gotten rid of them. There's a few little defects, but pretty much it follows the real boundary, so this will just generalize better. And the accuracy was on the test set. So, all right. And so there is a, you change the n estimators from 500 to 5. So if you do that, it will be much less accurate, and you get a flag that way. All right, and so now let's try Eta Boost. This is adaptive boosting, where you keep changing the weights to compensate. You perform 5 iterations of Eta Boost using a regularized SVM classifier with an RBF kernel, the way they did in your book. So here we go. And all I did was add the accuracy to this. So it's going to fit them, and then it's going to print the accuracy. And this is going to, I think, do 5 cycles. All right, this is the one that jerks for the high learning rate. This is the one that has a low learning rate. Yes, there we go. This is the one with the high learning rate, jerking all over the place, not really getting the answer. Here's this one converging nicely. And here's the accuracy of them. This one ends up only 67% accurate. This one ends up 87% accurate. As you'd expect, it really is reaching a better boundary to determine them. And so again, you change the learning rate and change the cycles, and you'll find you're able to get one that does an even nice smoother thing here, and the accuracy of that is the flag. So that's all I wanted to show you, where you get to run a few of these. They're very easy to set up and amazingly fast. You know, even 500 decision trees, you can see it runs in just a few seconds. So a lot of the reason why AI has come of age is because the hardware has gotten so good and fast. But the theory has gotten really fast too. All right, so I'm going to stop this.